Good morning and welcome to this geomorphology class. Last time we met, we were looking at continental drifting, plate tectonism, and seafloor spreading. Today, I want us to move on and we look at tectonism, because tectonism is one of the major internal earth movements, or the mother. Tectonism is the mother of the internal earth movements that have helped to shape a multiplicity of landforms both on the surface of the earth and within the crust. So when we talk of tectonism, we are simply referring to processes that take place from the interior of the earth, and these include faulting, warping, folding, and volcanicity. Of course, you realize that tectonic processes are initiated by tectonic forces, and the mother or the birth of tectonic processes or its origin are the convective currents that operate from the interior of the earth. Last time I did talk about the convective currents, and I said that these ones are generated as a result of heat and radioactivity from within the earth's mantle, because we know that the mantle is already fluid and semi-mobile. Then coupled with great heat and radioactivity, as well as geochemical and geothermal reactions, convective currents begin to move. He said these convective currents either move convergently, or they move divergently, or they are either rising or subducting. When you put water in a kettle, in a saucepan, and you begin boiling that water, when the temperature goes up or increases, that water will begin to move within that saucepan. The movement of that water is either from the center of the saucepan to the sides, or from the sides of the saucepan to the center, depending on where heat is greater. But as the heat increases, that water may even continue to move up and down, what we call rising and subducting. Therefore, at the end of the day, the tectonism and these convective currents will give birth to what we call tensional forces, which are a result of divergent movement of convective currents. They also give birth to what we call convergent or compressional forces, and then we have the rising and subducting, or the rise and fall at right angles. At the end of the day, these processes, of course, this movement of convective currents I've already mentioned, it gives birth to faulting, to warping, and folding. And then, of course, volcanicity, which becomes a secondary product of tectonism. So among the tectonic processes that we are going to look at, first of all, we'll look at volcanicity. I remember I did already mention about volcanicity when we were discussing rocks. And we say volcanicity is simply the activity, the process through which molten rock or magma makes its way onto the surface of the earth or into the earth's crust. This molten rock from the earth's mantle utilizes the lines of weakness that are left behind as a result of faulting, because faulting, like we shall define later, simply refers to the tear, the breakdown, and displacement of rocks along lines of weakness. Therefore, this molten rock makes its way along those lines of weakness. It is just like when those of you who have ever made charcoal, ever burnt charcoal there in your villages, when you put up that firewood and then you cover it with soil, and then of course there's great heat inside there, but if you come and make a hole somewhere in the side of that tunnel of yours of the charcoal, a lot of smoke will make its way through that. Because that smoke was held in there, it had no way to escape. But the moment you create an opening, it escapes. So it's the same thing which happens here. When faulting creates the opening within the crust, then the molten rock makes its way through those. Therefore, these lines of weakness develop downward in the crust and reach the magma. And the magma, which is already ready to move with a lot of pressure, high temperature, a lot of gases, eventually utilizes these lines of weakness. And like I did mention last time, volcanicity is either onto the surface of the earth, which gives birth to extrusive volcanicity, or into the earth crust, which gives birth to intrusive volcanicity. And therefore, intrusive volcanicity refers to magma or molten rock being forced into the rocks that make up the crust. It occurs when the lines of weakness, such as faults, joints, or bedding planes in the crust are existent. This magma fails to make its way to the surface of the earth because of loss of pressure and probably because every magma that leaves the magma chamber would wish to reach the surface of the earth. But because of loss of pressure, this magma eventually finds itself solidifying within the bedding plane, within the crustal blocks, and eventually leads to formation of intrusive volcanic features. These intrusive volcanic features, we have features like the batholith, which form at greater depths. We have the laccolith, which form at also relatively what we call intermediate depth, and we know laccolith. Then we have the lapolith, then we have the dikes, and then we have the seals. Dikes and seals, these ones form at shallow depth. And eventually when these ones are exposed, for example for the seals and dikes, they may lead to formation of trenches depending on the nature of resistance of the rocks. Extrusive volcanism, on the other hand, it refers to the extrusion of magma onto the surface of the earth. Here the magma has got sufficient pressure, sufficient temperature, and therefore it makes its way on the surface of the earth. I remember last time I told you that a volcanic eruption can either be silent or violent. But then what determines the violence or the silence of an eruption, I did mention that it depends on the nature of magma. And the nature of magma here, we are defining its viscosity. And we say the viscosity is defined by the amount of silica content in the magma. When the amount of silica is 65 and above, then that is acidic lava, and therefore it's also highly viscous. We define viscosity as the measure of resistance to flow. So when we say that magma is highly viscous, it means that magma cannot easily flow. So such highly viscous magma is associated with violent eruptions because it cannot come out of the surface of the ground quietly. Eventually, it is associated with violence. Whereas on the other hand, when we talk about basic lava, less viscous, it is associated with silent eruption because it can easily ooze out of the ground and then begin to flow. So the violence depends on the nature of the magma, depends on the amount of gases, depends on the temperature. When the magma has got sufficient temperature, sufficient amount of gases, sufficient pressure, it will make its way onto the surface of the earth and eventually leads to formation of extrusive volcanic landforms. These extrusive volcanic landforms are classified into the shield volcanoes or the basalt dome, which are characterized with gentle upper slopes, about 5%, and somewhat steeper lower slopes, about 10%. A shield volcano or basalt dome is a type of volcano usually built almost entirely of fluid lava flows. Fluid here we are talking about intermediate lava, 55% amount of silica. They are named for their low profile. That's why we call them basalt, because they have a low profile. They are not high-rise feature. They are quite low. That's why we are talking about gentle slopes on the upper, on the upper slopes, the angle. Then whereas on the lower slopes, it's about 10%. So we have these basalt domes as one of the, or shield volcanoes, as one of the most prominent features resulting from volcanicity. Shield volcanoes are composed of almost entirely relatively thin lava flows built over the central vent. So you find the magma coming and then flowing for a shorter distance and solidifying around the vent. And that's the reason as to why the slopes are not so steep, but they are quite slanting, they are quite gentle. The low viscosity, of course, of the magma, which is extruded in this case scenario, also contributes to the nature of the slopes, because the magma here is less viscous and therefore it has the ability to move for a shorter distance before it solidifies. Most shield volcanoes have a roughly circular or oval shape in map view, and very little pyroclastic material is found within the shield volcano. Shield volcanoes that form by relatively non-explosive eruptions. I told you that we have explosive and non-explosive. So these ones are usually formed by relatively non-explosive eruptions. And in this illustration given here, you can see that it has got very gentle slopes because the nature of magma that is extruded is less viscous, and therefore it can flow for shorter distances before solidifying. And we give the example of the Hawaiian shield volcanoes, which are found in the state of Hawaii. But we have these Hawaiian shield volcanoes. We talk about Kilauea, we have Mauna Loa, and with their characteristic oval shape in the map view. The next feature here we have the stratovolcanoes. Strato or composite volcanoes. These have steeper slopes than the shield volcanoes. Their slopes are over, sometimes go up to 30% in terms of angle. It's built by alternating layers of pyroclast and solidified lava. And here you realize that the steepness of their slopes is accounted for by the nature of the magma extruded. The magma here is highly viscous, acidic lava that solidifies immediately after reaching the surface of the earth. The alternating layers of lava and pyroclast form a composite or a stratovolcano with steeper upper slopes and gentle concave lower slopes. They grow to greater heights, sometimes going up to over 5,000 meters above sea level. They are shaded with parasitic cones, for example, the Mufumbiro ranges of southwestern Uganda, the likes of Oregon, the likes of Kilimanjaro, the likes of Kenya. These are composite volcanoes. Of course, the parasitic cones come about as a result of after an eruption has taken place, then there is a subsequent eruption, but then it finds the vent is blocked by the previous eruption. So this magma finds its line of weakness through the wall of the volcano and then extrudes on the side of the volcano to create what we call a conelet or a parasitic cone. Number 3, we have the ash and cinder cones. And we say these are largely constructed by pyroclasts, usually ejected from a central vent. Pyroclastic materials are extruded onto the surface during a gaseous explosion, piling the material around the vent. And just like the name suggests, ash and cinder, it means that this volcano is made up of layers of ash and cinder, where there is an extrusion of ash, and then on top of that ash, there is an extrusion of pyroclast, which now becomes the binding material. So that by the time if you remove this layer of pyroclast, just below it is just volcanic ash. So we have these features. The distinction about it is that for these ash and cinder cones are low-rise features, where they go above 500 meters in height above sea level, because they are usually associated with the other larger mountains. Examples are found within the areas of Kigezi, Ikisoro area. There are a lot of ash and cinder cones. You go to Oregon, those areas of Bududa, you also find ash and cinder cones created on top of the mountain. Sometimes some of them on top of the mountain, some of them just separate, but within that within that mountain region or environment. We have the lava plateaus or plains, which refer to features of monotonous flat landscape built by successive layers of basic lava. They result from an eruption of non-viscous lava from multiple fissures that bring onto the surface magma that flows widely over a large area. A lava plateau is monotonous terrain formed as a result of highly viscous magma or magma of low viscosity, which can afford to be extruded onto the surface of the earth and flow for longer distances before solidification takes place. So at the end of the day, you will find a landform created that is flat, monotonous. Then we have the craters and calderas. Craters are circular depressions, usually less than a kilometer, whereas calderas are also circular depressions, usually more than a kilometer, sometimes formed on the mountain summit. In this case, we have what we call mountain craters. So if we talk about mountain craters, we are referring those ones formed on the mountain top or mountain summit. They are usually circular in shape with a diameter ranging from 1 kilometer to 50 kilometers. Those are calderas. So calderas are usually larger. Last time I was asking you about the largest caldera. It's not you. I was asking the other guys of year 2. The largest caldera in East Africa, we have the Ngorongoro caldera, which is not, this one is not a mountain caldera for it. It's part of, like we shall be talking about, the explosion craters. So you have calderas. But how do they form? We know mountain craters form as a result of, can you explain using two theories? One of subsidence. that after an eruption has taken place, it has seized on top of the volcano material. There is a hollow vent that is left behind with no material. So what happens, the top of the volcano collapses material into the hollow vent, leaving behind a depression on top of that mountain. But it can also be formed as a result of a mountain top being blown off as a result of violent eruption, because there is subsequent eruption coming up, and then finds that the top of the volcano has been blocked by the previous material. So what happens is that the force of this eruption overpowers the summit of the volcano, and eventually it is blown off, leaving behind a depression. That depression is what we refer to as a mountain crater. When it is formed with water, it becomes a crater lake. And so the same scenario with calderas. We have lava-dammed depressions. A lava-dammed valley, or it's a valley blocked by magma from an eruption, formed when lava river valley, leading to water back ponding. That there is a river flowing, and then of intermediate back ponding upstream. It's a back pond. I remember those years when we would go to catch fish in those smaller streams. In our, what you would do, you would first go upstream the stream about 3 times, so that you have the chance that water is held up there, and you make sure that by the time that water overpowers the embankment of used to block the river or the stream, you have finished your fishing this side, because you must pour in to pick the fish by your hands. So eventually, during that process, if the embankment is weak and gives way, then the water will come and wash everything away. So what happens is that the magma comes and blocks or creates an embankment along the river valley, and then upstream the water begins to create a pond, what we call the process we call it back ponding. Eventually leads from lava dammed lake, the lakes of Bunyonyi. We found to capture upwards, you solidify is first piling around the vent and the forming very steep slopes. For example, we have the Moko ridges in Rwanda district. Just a minute, let me first connect power. So we have the volcanic ridges. Then you have the volcanic neck, formed from magma that solidifies within the vent of the volcano. After the formation, of course, of a volcano, magma moves up through the vent, but the eruption is seized before the magma reaches the surface of the earth, thereby solidifying within the vent of an active volcano, forming a volcanic neck. Later on, when it's exposed by erosion, then we have a solidified rock, such as Toro rock. That is a volcanic neck. We have hot springs and geysers. These ones, of course, a hot spring is a spring of warm water. Warm water above that is warmer above body temperature. And this warm water is formed when water saturates close to a slowly cooling igneous rock or magma chamber, thus getting heated, becoming less dense, and begins to rise to the surface of the earth to form a hot spring. Like, for example, the Sempire Hot Springs, Tagata, Minera, and on and so forth. A geyser, on the other hand, is a type of hot spring that periodically erupts. It's a periodic. It's seasonal. It's not permanent, like the likes of Sempire, which are permanent. You go there today, you go there tomorrow, you find the same scenario. So the same way like a hot spring is the geyser, but only that geysers are periodic. So we have those features. And of course, maybe lastly, which is not mentioned here, are explosion craters. Explosion craters are features, are depressions formed on the surface of the earth, but they are formed as a result of a highly explosive eruption that magma builds within the magma chamber, and then it finds no line of weakness per se, so that the magma can easily make its way to the surface of the earth. But what it happens is just like the word explosion suggests. So those of you who have ever seen a bomb explosion in a movie, I know you have not seen it in reality. So the magma explodes at once, pushing away the layers of the earth and pyroclasts onto the sides, eventually creating a depression, which depression is what we refer to as an explosion crater. That explosion crater, when filled with water, becomes an explosion crater lake. Like Lake Katwe is an explosion crater lake. Lake Chigere, Lake Wabikere, Lake Chikorongo, Lake those lakes in Rubirizi, Bunyaruguru Hills, those are explosion crater lakes. All these are features resulting from extrusive volcanicity. Apart from volcanicity, of course, the other product of tectonism is faulting. We define a fault as a line of weakness or a planar fracture through a rock. Faulting is the physical breakdown or displacement of rocks along fault lines. It takes place in different forms. We have a normal faulting. This is by tension. Reversed faulting. This is by compression. And tear faulting, which is a result of both tension and compression. What are the landforms that result from faulting? One of them is the Rift Valley. And I know this one we are very conversant with it. We know very well that a Rift Valley is an elongated trough. A Rift Valley is an elongated trough bordered by escarpments on either sides. This elongated trough is one of the most prominent features of the Earth's surface, more so in Africa and in East Africa particularly. This elongated trough, of course, is formed as a result of faulting. And this faulting, like I've said, it can be tension, can be compression. Compression forces, what we call pushing together, bring about the cracking of the crust block to form what we call reverse faults. And the continued compression implies that the side blocks will override the central block. They override the central block. But the central block, because it's now left alone, sinks to maintain equilibrium. And that sinking leaves behind a depression, which we call a Rift Valley. On the other hand, tension, continued tension, pulling apart, leads about the fracturing of the crust blocks, or the crust, bringing about what we call normal faults. And continued tension, pulling apart, ensures that the side blocks move away, leaving the central block alone. The central block sinks to maintain equilibrium, leaving behind a depression, which we refer to as a Rift Valley. That is faulting, bringing about creating landforms. And we have the eastern arm of the Rift Valley here, which runs through Kenya, attributed to tension forces. We have the western arm, attributed to compression forces. But there are other processes which would explain this, which we shall discuss during the interactive session. Then we have the block mountain, or host, what we call it, which is referred to as a faulted highland, bordered by a series of steep slopes, formed due to compression forces, or differential uplift, or relative sinking and rising. Whichever process you want to use, all this can help us to explain the formation of a block mountain. Faulted grabens, these ones we said they are depressions formed on the Rift Valley floor as a result of localized secondary faulting on the Rift Valley floor. The same process which led to the formation of the Rift Valley leads to formation of the faulted graben. Only that grabens are localized. They are not elongated troughs. So we have those grabens, the likes of those Rift Valley lakes, like we know, or like you can mention them. We have the fault scarps or escarpments, generally steep slope formed when a block of land moves relative to the other, leaving one behind and rising. There is relative rising, or differential uplift. One block moves, this is a crustal block, but there is a fault line in between here, a normal fault or a reverse fault. So one block moves relative to the other and creates a steep slope here, which we refer to as an escarpment, for the likes of Butiaba in western Uganda. And then we have the fault-guided valley, which is referring to an elongated depression that follows the cut line or the outline of an original fault. That when tension and compression take place, we have tear faulting, and this tear faulting brings about, when it encounters a weak geological structure, it brings about a tear fault within the crust, within the ground, the surface of the earth. This tear fault is eventually widened as a result of erosion and the like, those subsurface, those denudation processes. But if it so happens that this tear fault is formed across an already flowing river, across the long profile of a river, then river capture is going to happen. As this tear fault widens, the river abandons its original course and begins to flow, following this outline of a fault line, and such a river will be called a fault-guided river. For example, River Aswa. Thank you so much. I will explain the others when we meet for this live session. I wish you a good day.